Imagine finding out that the most unpredictable, like violently impulsive person you know is actually secretly a master watchmaker.
Right.
I mean, that is the exact paradox we're diving into today. You've pointed us toward an element that, well, you probably never think about. It's just sitting quietly, or actually not so quietly, at number 37 on the periodic table.
Yeah, definitely not quietly.
Right. Rubidium. So the mission for today's deep dive is to figure out how a metal that literally explodes when it touches water somehow became the silent, hyper-precise timekeeper of modern global civilization.
It really is. I mean, it's the ultimate chemical contradiction.
Yeah.
Because on the surface, rubidium is just this soft, silvery white alkali metal. Like if you held it in a glass vial, it would look completely
So
unassuming.
it's a shiny rock.
Exactly. But it exists on this absolute knife edge between, chaotic, impulsive chemistry on one side and then pristine atomic level precision on the other.
Well, before we get into how it runs our GPS systems and all that, we really need to understand where something this strange even comes from. Right.
Because, I mean, you don't just find chunks of pure rubidium sitting around in your backyard. And it wasn't even formed at the beginning of the universe, right?
No, not at all. The Big Bang basically just gave us hydrogen, helium, and, well, a tiny bit of lithium.
Uh-huh.
Everything heavier had to be cooked up later. So rubidium is what we call a later generation element.
Meaning what exactly?
It requires the really intense environments of dying, highly evolved stars to even exist. It's formed through this mechanism called the slow neutron capture process.
Okay, slow neutron capture. You're going to have to unpack that for us.
Right.
What is actually happening inside the star?
So deep inside these massive aging stars, you have atomic nuclei that are constantly bumping into this sort of soup of free-floating neutrons.
Like a crowded room of particles.
Yeah, pretty much. And every so often, a nucleus will capture one of these neutrons. It just absorbs it. But because this process is slow, and by slow, I mean it happens over hundreds or thousands of years, not in some split-second explosion.
The nucleus actually has time to figure out if it's stable or not. And if absorbing that neutron makes the nucleus unstable, one of its neutrons will literally decay into a proton.
Oh, and changing the number of protons changes the element itself.
Exactly. It just steps right up the periodic table, element by element, over thousands of years.
Wow.
Yeah. And eventually, this slow cosmic conveyor belt produces rubidium. Then, when those mature stars finally die and go supernova, they blast these newly forged elements out into the cosmos.
So literally every atom of rubidium on Earth was forged inside a dying star and blasted across space.
Yeah.
Which, explains why it's here. But what's weird to me is how it's distributed. Like, I was reading the source material, and it says it's in granite, it's inside meteorites, there are even trace amounts dissolved in seawater.
It's all over the place.
Right. It's actually more abundant in the Earth's crust than copper or zinc. But wait, if it's everywhere, why don't we ever hear about massive rubidium mines? We have copper mines.
Well, that's because rubidium is, it's basically a master of geological camouflage.
Camouflage.
Yeah, so copper and zinc will bond with other elements to form these really dense, concentrated veins of ore. You can just dig them up.
Okay.
But rubidium almost never forms its own specific minerals. Instead, it plays this endless game of hide and seek by chemically mimicking potassium.
Wait, how does an element just mimic another element in a rock?
It really comes down to physical size.
Mm-hmm.
The chemistry of a mineral crystal is basically a three-dimensional jigsaw puzzle. The pieces have to fit perfectly.
Right.
Well, the ionic radius of a rubidium atom, like the actual physical space it takes up, is incredibly close to the size of a potassium atom.
Oh, I see. So when the Earth is cooling and forming crystals, the crystal lattice reaches for a potassium atom but accidentally grabs a rubidium atom instead.
That's it, exactly. Just slots right into the structure. The crystal doesn't care because the fit is close enough.
That's wild.
Yeah, so because of this, its geological identity is entirely subtle. It's a hitchhiker.
Just hitching a ride.
Right. When mining operations extract lithium or cesium from complex pegmatite rocks, minerals like lepidolite, they'll just find trace amounts of rubidium sneaking in exactly where potassium or lithium were supposed to be.
Okay, so if it's physically identical to potassium and hiding inside these rocks, it makes me wonder what happens when a chemist finally, rips away that camouflage and isolates the pure metal.
Well, that is where the element's volatile personality really takes over. And honestly, volatile almost feels like an understatement here.
Uh-oh.
Yeah. Once you strip away the rocks and isolate pure rubidium, it becomes exceptionally reactive. It all stems from its electron configuration.
The way its electrons are arranged.
Exactly. Rubidium is an alkali metal, and it has one single electron in its outermost orbital, the fifth shell. Chemists call this a 5s1 configuration.
Right, and atoms like balance. So I'm assuming having one lonely electron sitting way out on the edge of the fifth shell is not a stable setup.
It is the absolute opposite of stable. I mean, the nucleus is positively charged, right? So it's holding on to the negatively charged electrons.
Sure.
But that outermost electron is so far away from the nucleus, and it's shielded by all those inner rings of other electrons, that the nucleus is barely holding on to it. It's just hanging by a thread.
So it wants to get rid of it.
Desperately. The atom is desperate to ditch that single electron so it can drop down to a perfectly full, totally stable inner shell.
And because it's so desperate to get rid of it, it just throws it at whatever it comes into contact with.
With violent enthusiasm, yes.
Mm.
If you take a piece of pure rubidium and, say, drop it into a bowl of water, you don't just get a little fizz.
I'm guessing not?
No, the rubidium instantly attacks the water molecules to strip away the oxygen. It forces that loose outer electron onto the water, ripping the H2O apart.
Oh.
Yeah, this creates rubidium hydroxide, and crucially, it releases hydrogen gas.
And I'm guessing all that aggressive chemical bond breaking releases a ton of energy, too.
A massive amount of heat is generated in just a fraction of a second. So think about it. You have a sudden spike of extreme heat right at the exact moment you're releasing highly flammable hydrogen gas.
Oh, wow. Which means the hydrogen immediately catches fire or just outright explodes.
It explosively ignites. It is a sudden, incredibly energetic reaction.
Mm.
And what's wild is if you vaporize rubidium in a flame, it doesn't give off a standard orange fire.
What color is it?
It burns with this famous, stunning, deep red-violet, almost crimson-purple color.
It's highly theatrical. Like, if krypton is hidden light, rubidium is unstable excitement.
Totally.
It's the emotional extrovert of the alkali metals. Like, it's beautiful, but totally impossible to ignore once it's activated.
Right. Once you set it off, you can't ignore it.
But wait, since we just established that rubidium is a physical mimic for potassium, and, humans and plants are basically packed with potassium.
Yeah, we need it to survive.
Right. So what happens when this volatile, explosive metal actually enters the biological world?
Well, thankfully, it doesn't spontaneously combust inside you.
That's a relief.
Yeah. Biology operates in water, so any rubidium you encounter in nature has already reacted and stabilized into an ion. But the mimicry continues.
How so?
Well, rubidium has absolutely zero essential biological role. Life on Earth evolved completely without needing it.
Okay.
But biological systems, just like those crystal structures in rocks, can't easily tell the difference between potassium and rubidium.
Oh, I see. So it's like the cellular bouncers just see a mineral that's roughly the size and shape of potassium, and they just wave it into the club.
Exactly. Plants, microbes, even human nervous systems will just absorb trace amounts of rubidium ions. Now, in tiny environmental amounts, it doesn't matter.
Right.
But science actually uses this biological blindness to our advantage.
Right.
And we need to track how blood flows through the heart muscle or map out potassium pathways in neuroscience experiments.
We use rubidium.
Yeah, researchers will use radioactive rubidium isotopes as a medical tracer. The body just treats it like potassium, allowing us to map the whole system.
So it's basically a biological imposter. It puts on a potassium name tag and sneaks right past the bouncer.
Yep, that's exactly what it does.
But what happens if you take in too much? I mean, if it's sneaking into the potassium channels, eventually that has to cause, like, a traffic jam.
Well, it wrecks the machinery. Your nervous system and your heart rhythm rely on very tightly regulated potassium channels to fire electrical signals.
Right, keeping the beat.
Right. So if a large dose of rubidium floods the system, it jams up those channels. The fit is close, but it's not perfect. So it disrupts the biological ion balance, leading to real neuromuscular issues.
That sounds dangerous.
It can be. Its entire identity in the natural world is really about imitation rather than necessity.
Okay, let's step back for a second and look at the portrait we've painted here. Because rubidium is a late-blooming cosmic byproduct. Geologically, it's a hitchhiker. Chemically, it's an explosive, highly reactive extrovert. And biologically, it's an imposter.
That sums it up.
So how on earth do we arrive at the great paradox of this deep dive? Like, how did this specific chaotic metal become the backbone of modern digital synchronization?
Well, the shift happens when human civilization reaches a point where we need to measure time not in minutes or seconds, but in billions of a second.
Wow, okay.
Yeah. For most of human history, rubidium was practically useless. You couldn't find it, and if you did, you couldn't tame it. But today, it's what we'd consider a Tier 3 or Tier 4 specialized element.
Meaning we don't use it for everyday stuff.
Right, we don't build skyscrapers out of it.
Hmm.
But our high-tech infrastructure relies on it heavily. And its absolute crowning achievement is the rubidium atomic clock.
Wait, hold on. We just said dropping it in water causes a fiery purple explosion.
We did.
It's chaotic. It's like harnessing a lightning bolt to power a metronome. How do we get highly accurate, incredibly disciplined measurements of time from something so emotionally unstable?
That's the brilliance of it. We are bypassing the macro-level chaos entirely.
What do you mean?
When you put a chunk of rubidium in water, you are watching trillions of atoms desperately reacting all at once. But in an atomic clock, we isolate a tiny vapor of rubidium inside a controlled, perfect vacuum.
Okay. No water, no oxygen.
Exactly. We strip away everything that allows it to react.
So we basically put it in a sensory deprivation tank.
Yes.
All right.
And once it's completely isolated like that, we stop looking at its chemistry and we start looking at its quantum mechanics.
Oh boy. Okay, quantum mechanics.
It's not as scary as it sounds. Atomic clocks don't use gears or springs or even quartz crystals. They measure the exact frequency of electromagnetic radiation required to make that single, lonely 5s1 outer electron.
Wait, the one hanging by a thread?
That's the one, to make it flip its spin or jump between energy levels.
Ah, so the exact same loose electron that causes the massive explosion is what we're measuring.
That specific electron is the absolute key. Inside the vacuum, scientists bombard the rubidium vapor with microwaves. And if you tune the microwaves to the absolute perfect frequency, that outer electron will absorb the energy and jump to a higher state.
And if the frequency is off?
If the microwave frequency drifts even a fraction of a percent, the electron won't jump at all.
So the tick of the clock isn't a mechanical movement?
No.
The tick is the exact, unvarying frequency of microwaves needed to make that specific electron jump.
You've got it. That energy transition is a fundamental law of physics. It literally never changes. Every rubidium atom in the universe behaves exactly the same way under those conditions.
It is just wild.
So the clock constantly tunes its microwave generator to maximize the number of jumping electrons. And that microwave frequency becomes your hyper-precise metronome.
I know cesium atomic clocks are, considered the absolute gold standard for measuring time. Does rubidium beat cesium?
Well, cesium is slightly more precise, technically, but cesium clocks are generally larger, much more expensive, and harder to maintain.
I see.
Rubidium clocks hit the perfect sweet spot. They are incredibly accurate, losing maybe a second over decades, but they can be made astonishingly compact and cheap.
Really? How compact?
You can shrink a rubidium oscillator down to fit onto a microchip.
Oh, wow. So because they are compact, we can launch them into space, on GPS satellites.
Exactly. They are the beating heart of GPS.
Yeah.
Your phone's navigation works by measuring the exact time it takes for a signal to travel from multiple satellites to your device.
Right.
If the clocks on those satellites are off by even a microsecond, your location on Earth is off by hundreds of feet.
That would be a problem.
A huge problem. Rubidium clocks provide the frequency standards that power telecommunications. They sync up global server networks, and they allow financial markets to execute high-frequency trades without colliding.
So humanity took the most volatile element, locked it in a vacuum, and listened to its heartbeat to synchronize the planet.
That's pretty poetic when you say it like that.
It is. But tracing these atomic rhythms doesn't just stop at timekeeping, does it? Because the deeper we look at that electron, the weirder the science gets.
Oh, it gets so weird. It leads straight into the strangest frontiers of modern physics.
Huh.
Rubidium is heavily used in quantum mechanics experiments, specifically in creating what's called Bose-Einstein condensates.
Okay, you're losing me. What is that?
It involves taking rubidium atoms and cooling them down to temperatures just a tiny fraction of a degree above absolute zero.
Wait, how do you cool something down that much, practically?
What a process called laser cooling?
Hold on. Laser cooling.
Yeah.
Lasers are just focused beams of intense light. They burn things. How does shooting a hot laser at a metal freeze it?
I know, it sounds totally impossible. But you have to think about what heat actually is. Heat is just atoms moving around.
Right.
If an atom is moving fast, it's hot. If it's completely still, it's at absolute zero. Well, lasers don't just have heat. Photons of light carry actual physical momentum.
Like tiny microscopic billiard balls.
Exactly. Imagine a bowling ball rolling down a bowling lane. That's a hot rubidium atom.
Okay.
Now imagine throwing thousands of ping pong balls at the bowling ball, hitting it dead on from the opposite direction.
The ping pong balls will bounce off, obviously, but every impact will slow the bowling ball down just a tiny bit.
Right. Scientists use precisely tuned lasers, firing photons at the rubidium atoms from all directions.
Oh, I see.
Yeah, as the atoms absorb and re-emit the photons, they lose their forward momentum. They slow down to a crawl. And because temperature is just movement, slowing them down brings them to almost absolute zero.
That is genius. And what happens to rubidium when it gets that cold?
Common sense breaks down entirely. The atoms stop behaving like individual particles of solid matter. Their quantum wave functions actually expand and overlap.
Wait, they overlap?
Yeah, thousands of individual rubidium atoms merge into a single, massive quantum state. They basically behave like one giant superatom. It's a state of matter where they move as a wave instead of as particles.
Okay, so let me get this straight. We take a metal that naturally wants to explosively catch on fire in a tiny puddle of water, and we blast it with lasers until it literally freezes into a localized quantum wave.
Yep.
The irony is staggering. But getting this element into those high-tech labs and satellites, it has to have earthly consequences, right?
Very real consequences. We talk about, quantum waves and pristine vacuums, but to get the rubidium, you have to actually dig it out of the dirt.
Right, the hide and seek.
Exactly.
Yeah.
Because it's a trace element, hitchhiking in other minerals, you can't just mine a neat little vein of it. You have to extract and crush massive amounts of rare earth and pegmatite rocks, usually while mining for lithium, just to isolate a tiny usable fraction of rubidium.
So to build our incredibly compact atomic clocks, we actually have to endure a massive industrial footprint on the other end.
The footprint is heavy.
Huh.
And once you process it, you are left with extreme chemical handling hazards.
Yeah.
Like we discussed, pure rubidium catches fire in the air.
Yeah, you can't exactly ship it in a cardboard box from Amazon.
No, definitely not. It must be transported and stored under vacuum or completely submerged in inert mineral oil. So the global supply chain to get this element from a lithium mine into a GPS satellite is incredibly specialized, totally niche, and heavily dependent on just a few specific processing facilities around the world.
Wow. It really forces you to step back and look at the invisible infrastructure we've built.
It really does.
I mean, we've constructed this entire modern world of invisible synchronization, financial markets executing thousands of microsecond trades, global data transfers pinging across oceans, the GPS that literally lands commercial airplanes. All of it is resting quietly on the shoulders of this reactive violet metal.
It is the ultimate symbol of order emerging from chaos. I mean, it proves that volatility doesn't prevent precision.
Right.
By isolating and deeply observing a system that desperately wants to be erratic, we've actually unlocked the deepest forms of precise measurement humanity has ever achieved. Nature doesn't have to be perfectly calm to be perfectly measured.
That's beautifully said. You know, before we wrap up today's deep dive, there's a really beautiful, almost poetic duality here from the source material that's definitely worth sitting with.
Oh, is that the dating?
Yes. So we've talked extensively about timekeeping, right? How we measure the immediate tiny fractions of a second in our daily lives using this element.
Right, the atomic clocks.
But rubidium actually has a naturally occurring radioactive isotope, rubidium-87. And over an incredibly long timeline, like billions of years, rubidium-87 slowly, steadily decays into an entirely different element, strontium-87.
Yeah.
And geologists actually use this specific decay process for radiometric dating. They measure the ratio of rubidium to strontium in planetary rocks to determine exactly how old the Earth and even the Moon actually is.
It's amazing.
It is. I just want you to think about the sheer scale of that for a second. Here is a single, violently explosive element. On one hand, humanity isolates its electron frequencies in atomic clocks to perfectly measure the fleeting, immediate microseconds of our present. And on the other hand, the planet uses its slow radioactive decay as this massive cosmic hourglass to measure the billions of years of deep, ancient planetary history.
That's incredible.
How strange and honestly how wonderful that our grasp on the immediate present and our understanding of the ancient past both rely entirely on the exact same volatile metal.
It really makes you look at the periodic table a little differently.
It definitely does.